Yeah, I'll be talking about how supermassive binary black holes are, how they accrete, and the electromagnetic signatures that they have. And I'm basically going to be focusing on the science results that we've accomplished this year, because I think the technical details I'm happy to talk about at the conference. Come talk to me. But I think we achieved a lot this year, most because of the great team we have. So we have a number of great researchers, primarily at RIT. So Mark Avar is here, and Dennis Bowen, who couldn't make it, and Stefan Dascali, who helped with the ray tracing, the post-processing of the simulation data, and Vasilius Muez. And as they come onto the job market, please look for them, because they're great and you should hire them. So we'd be really sad to see them go, but that's, I guess, how academia works. So this is based on papers here that we've listed. We just submitted the post-processing ray tracing paper. So look for that on the archive soon. So basically what we have are two supermassive binary black holes. So these are black holes that live at centers of galaxies. They become binaries as the galaxies merge, and these are millions to billions times the mass of the sun. So I hope everyone has heard of LIGO. So you can't use LIGO to detect these binary black holes with gravitational waves, because they operate at much lower frequencies, because they're more massive, and so they orbit at much longer timescales. And so you have to really put LIGO in space to get rid of the seismic noise limit, and you have to separate them out, the interferometers, out to greater distances, and then it becomes something called LISA. And so that's a NASA mission that is going to operate in the early 2030s, maybe earlier. And so we're going to be looking for these things in the gravitational wave sector with LISA. We can also look for them with pulsar timing arrays. So depending on the mass of the binary, it sweeps a whole range of frequencies. And so you can also look for them in pulsar timing arrays. So this is little wobbles in pulsar timing, or the time between pulses of pulsars or neutron stars. And so you can use that to identify gravitational waves. Anyway, so what we want to do is, we're impatient. We want to look for them with light, so that we learn about them before we actually have to look for them in gravitational wave bands. And we want to learn about them. And primarily, these are the best candidate for counterport sources for LISA. So because these are binary AGN, they're very bright. So we hope to actually see them in light. So this is the multi-messenger best candidate for LISA. And, but we're also going to be looking for them with large sky synoptic telescopes like LSST that survey the sky at high cadence, and hopefully can identify them through their variability and spectral signatures. So what we really need to do is, in order to differentiate these sources from like just regular AGN, we need realistic simulations to really see what the key signatures are of these binary systems. So the basic strategy that we're operating with is that we want to do kind of a zoom in. Ideally, we want to start with galaxy simulations, and then nested in a nested way zoom in. We start in the post-Newtonian regime, so where the black holes are inspiraling, so that the separation is shrinking due to gravitational wave reaction, and we do that. We do circumbinary disk simulations where we excise the inner region to prevent, to get around the Courant limit, to not resolve the finest levels, spatial levels and time levels near the black holes. And that allows the circumbinary disk to relax, so that we have a good relaxed mass reservoir to do simulations in which we actually simulate the scales of the event horizon. And we can form mini disks and evolve those mini disks. And we can see the interactions between the mini disks, which circulate around each black hole, and the circumbinary disk that circulates around the whole system. So we use GRMHD techniques, but the gravity is post-Newtonian. It means we solve Einstein's equations perturbatively. And so we can use the background calculation, the harm code that just assumes that you have a metric. So So we use the HARM3D GRMHD code. And some of the novel techniques that we've had to develop are dynamically warped grids. So this is like a spherical grid that looks like spherical at large radius, but near the black holes, they become locally Cartesian-like. So we're pinching the cells near the black holes to resolve the MHD there. And that allows us to resolve the mini disks well around the black holes, but also to use a similar topology of the disk in the circumbinary region so that we preserve angular momentum really well. And so the key challenge is really to resolve these large length scales in the system. So as I said, we start with circumbinary disk data, and then we have to interpolate onto a different grid that has the black holes on the grid. And so we call those bog simulations. And those little warps track the black holes. So that interpolation, okay, it's not that technically advanced, but what makes it difficult is that we have magnetic fields, and we have to satisfy this constraint called the solenoidal constraint. There are no such thing as magnetic monopoles yet, so we have to prevent them from arising on the grid. And so we have to actually clean the grid of magnetic monopoles, and this is not trivial on a dynamically warped grid. So we do this at the initial time, and then we're free of monopoles, and then we use the standard constraint transport techniques. So really this has allowed us to do the first resolved GRMHD simulation of mini disks and how they interact with circumbinary disks. So one of the benefits of working with Blue Waters is that of the wonderful staff that it comes with. Mark Van Moor, who's sitting over there looking all modest, has actually worked with us and developed some really great visualizations of our simulation data. We're very grateful for his involvement in the project. So what you're seeing here are the mini disks and the circumbinary flow, but you're also seeing the magnetic fields that come from the mini disks. So these are, so the white lines are magnetic field lines, but those magnetic field lines are seeded at points that are vected with the flow, so that there's a consistent set of magnetic field lines throughout the whole movie. There's some tricky business with reseeding and stuff, but as the seeds live on the grid, some seeds could accrete and fall into the black hole, in which case they don't emit a magnetic field line anymore. So there are all these really sophisticated details that Mark had to work out, and I think the results look spectacular. So.
Can I ask a quick question? Do you evolve the seeds as part of the simulation
We,
or as part of post-processing?
Yeah, as part of post-processing. Yeah, we use the velocity, but yeah, that's something we want to do to create even better visualizations in the future. Yeah. So this is a closer in view of density contours, actually renderings of through the density material. And what you're actually seeing is, so we start with pretty massive mini disks. They drain relatively fast because of the shallow gravitational potential of the binary. So it becomes shallower as a binary becomes closer due to relativistic effects. Excuse me? They drain into the black hole, so the material drains into, yeah. But they refill. So as there's this overdensity region in the circumbinary disk that rises at late times in the circumbinary evolution, and this overdensity or lump orbits the binary. And as the black holes pass by that lump, it pulls in extra matter from that lump. And so you get this refilling and draining effect. So one black hole will pick up and fill up its mini disks, and then as it orbits away from the lump, it'll drain, but then you get the next one. And so this dynamical draining and depletion effect was not really thought of until we actually did the simulation. So it gives rise to a potential periodic signal that we hadn't thought of before. So we looked at the azimuthal modes of density, so the relative strengths of those modes. So in some prior work by our colleagues, they focused in on a mini disk, and they did this in a Newtonian semi-relativistic way. And they found that spiral waves arose. These are m=2 spiral waves, and those created spiral shocks that allowed really efficient angular momentum transport into the black hole. We see, though, in the relativistic regime where you get really close with the really close binaries, that the m=1 mode is inspired more than you would normally expect. So m=2 and m=1 are both really strong. And the relative strengths of those increases with time. So we're seeing departure from Newtonian regime situations in the relativistic regime. So that's really exciting. And that also will inform us what sorts of electromagnetic emission may arise from these disks. And so we did 3 orbits of the mini-disk simulation. The 3rd orbit was done this past year on Blue Waters. We've been focusing on new simulations, which I'll talk about in a moment, and also we've done post-processing radiative transfer calculations from the mini-disk simulation. So what we do is we assume that there's some sort of photosphere. So we identify a photosphere in our simulation. That photosphere emits at a thermal black-body spectrum, and then that spectrum is then transported through a corona that has a non-thermal component with a fixed temperature of 100 keV for technical reasons that I can explain later. But and then we scale the density to explore the optically thin and the optically thick regime. So here, this is light from the optically thin regime where light isn't really absorbed much by the material. Okay, so this allows you to see all the cool light bending effects that happen when light is transported from the vicinity of one black hole and is warped by the other black hole. So you can see lensing from the emission of one black hole by the other black hole. And so what we're really after, though, is a spectrum. So this is the first spectrum arising from a GRMHD simulation of accreting binary black holes with many disks. And since we have time data, we can show how it evolves in time. And so we can hopefully look for these fluctuations in the spectrum in actual systems and use the way that the spectrum is fluctuating to recognize that they're a binary black hole. And if we have more of these simulations with more mass ratios, more spins, then we can use that information to then to extract orbital and mass parameters, spin parameters from the system. And so this is just really starting off that long-term campaign that we hope to engage in soon. But it's really exciting. So one key feature of this is that the mini disks create like their own thermal peak. Okay, and so sometimes you'll see that this thermal peak is strong enough that it creates this little dip in the thermal peak that you usually don't see, and could be a means to identify these as binaries. And that little dip is, the technical term is called a notch. We love really sophisticated vocabulary here. And that notch deepens, becomes more obvious when the black holes are spinning and they're further separated. So unfortunately, our simulation was too close, and the black holes were not spinning. So we hope that in future simulations, that notch is going to be more recognizable and then maybe more easily seen in observations. And so since we only had 3 orbits of data, we can't really justifiably give you a light curve. And so as a proxy of kind of the source of variations you would expect on the course of an orbit, we looked at how the luminosity changed as a function of phase of the orbit. So here, these are different levels. So these are light curves, so to speak, as a function of the phase of the orbit at different inclination angles. So the bottom one is you're seeing the disks edge on, and then you're becoming more face on. and these lines are shifted. They would all lie really close to each other on this plot, but they're all shifted so that you can see them. And so you see that there's larger variation when they're edge on, and that's due to the lensing of the background black hole emission by the foreground black hole. So the brightest emission comes when the black holes are aligned with the line of sight. And it's not too surprising. And you're not seeing, when they're face on, you're not seeing any significant variation, and that's just because there's no orbital variation on a face-on view due to lensing or to relativistic motion. But there would be time variability there because of the transits, the time-dependent transits of the black holes with the overdensity. So this doesn't pick up that kind of variation, that kind of temporal variability. So this is just the phase variability. So in the future, we hope to actually do longer-term simulations so that we can actually give you a light curve. So the bulk of our computational resources were spent doing the first tilted circumbinary disk simulations with MHD and 3D, and these were performed by Mark Havara, and they're hot off the presses. We still need to analyze them, but we've been able to produce some really cool movies recently, so I'll show you that. They're shrinking. The binary starts off at a relatively large separation and shrinks over the course of the simulation. So you'll see that shrinking happen. And these are the parameters of the simulations. We do 0, 6, and 12-degree tilts. And so this is the movie that Mark made just today. And so it starts off slow, and then you can see that this is the tilt. So we're seeing the disk at an inclined view, but the tilt is apparent as it's going diagonally here. And so tilted disks are really cool because the precession, the rate of precession varies as a function of radius. So the innermost region warps faster than the outermost regions. And so you get this differential precession gradient that then can create these shear layers that then can maybe align the disk with the black hole, or here the binary. So black holes spin, that's an angular momentum vector, but also the time averaged orbital motion of the binary is an angular momentum. So they operate similarly. So later Sasha will talk about how really warped disks around spinning black holes operate. And we hope to maybe connect how these two different systems may operate similarly or differently based upon the nature of that angular momentum vector. So one thing that we're trying to look for is how that binary interaction with the lump changes when the tilt changes. So you see they're getting really close, and so that's why the orbital motion speeds up. So we looked at the m=1 modes, so the azimuthal modes. So m=2 is there because of the binary, and then m=1 is the lump. So we see that the lump is still pretty strong there, and so but it still seems to look a little bit different. So our next set of simulations will be using this MHD patchwork code. So we have different patches. They can be misaligned. They can have different coordinate systems. I want to show you a test where you have magnetic field components. There's a MHD wave that goes through two patches. And you have to treat the magnetic monopoles, the constrained transport carefully here. So if you only use the typical flux CT or constraint transport scheme, you develop monopoles on the interpatch boundary that completely ruin the simulation. But if you do fancy tricks that Mark has developed, you can dissipate those monopoles, and you can then perpetually transmit MHD waves through an multi-patch domain. And so he's also done this in a black hole context. So you have a black hole, and you have three patches. You have a spherical patch, and you have two polar patches that eliminate the coordinate singularity there. And he's found that this works very well in a relativistic context. So I just want to put up the summary and conclusions and leave you with the nice movie. And so I just want to thank Blue Waters for these wonderful resources, both computational and also person-powered. So thank you very much.